Okay, Assalamualaikum and good day. So in this video, we will look at an example from final examination paper July 2017. Okay, given to us that x equal to 0 is a regular singular point. Okay, here right now, x equal to 0 is a regular singular point. For the differential equation given xy double prime minus 4 plus xy prime plus 2y equal to 0, we need to show that the recurrence relation is as given as such here, and then hence we need to find the general series solution of the differential equation up to the term x power of 7. Automatically, when you see x power of 7, you will think that you need to find until a 7. But for this question, there is a little trick here, which means that you don't have to find until a 7. Okay, so the first step will be, as usual, since it is a regular singular point, we will apply the Frobenius method. Which is, we let y equal to summation an x power of n plus r, and y prime differentiate y with respect to x, and y double prime is differentiate y prime with respect to x. Okay, and then the next one, we substitute y prime and y double prime in the given dE. As such, we have x, the summation for y double prime, minus 4 plus x, summation of y prime, plus 2, summation for y. And then next, what we need to do is expand the equation. Okay, expand the equation. Okay, you will have, that means we multiply x with x power of n plus r minus 2. We will have x power of n plus r minus 1. And here, minus 4 multiply with the summation. And x also we need to multiply with the summation. Don't forget, you need to multiply with the negative here. Okay, the operator in front of the summation. Okay, and then this one, nothing changed for the last term. Okay, next, equate this equation here to the smallest power. The smallest power will be x power of n plus r minus 1. So nothing need to be done for the first term, second term. But for the third term, we have n plus r, right? So we need to change it to n plus r minus 1. So for an, it will be an minus 1. And here, n plus r will be n plus r minus 1. And our summation will also start at n equal to 1. Okay, for the last term, changes need to be done here. So it will be x power of n plus r minus 1. We will have an minus 1. And our summation here will start at n equal to 1. Okay, next. As usual, you need to find the initial roots. Initial roots is when n equal to 0. Okay, that means we just need to use the first and the second term only. Okay, we have r minus 1 minus 4 times r, okay, in bracket, multiply with a naught equal to 0. Therefore, we have r squared minus r minus 4r equal to 0, since a naught does not equal to 0. Okay, simplifying, and until then we will have r1 equal to 0 and r2 equal to 5. Please remember, r1 should be the small value of r. Okay, as you can see here, r1 is an integer, r2 is also an integer, where r2 minus r1 modulus is equal to 5 minus 0 modulus, that is 5. Okay, positive integer means case 3. But here, we don't know yet. It's either 3a or 3b. Okay, proceed to the next step. You need to find the recurrence relation. The recurrence relation will start when n greater than or equal to 1. Refer to your last summation. Last equation for the summation. Okay, so from here, okay, we have the clue here. r minus 5, the factor, right? So that's why here it will be n plus r minus 5. Substitute n plus r in the place of r. Okay, since it is r, so it will be n plus r minus 5, n plus r minus 5 for an. Okay, and then minus just rewrite. That means the first thing we have what? N plus R minus 1 an minus 1 plus 2 an minus 1. Therefore, here it will be minus n plus r minus 1 an minus 1 plus 2 an minus 1 equal to 0. Simplifying this, we will have an equal to n plus r minus 3 over n plus r times n plus r minus 5, an minus 1. Okay, so we have shown the recurrent relation, we have proved it. The next thing is, okay, here. We need to substitute the small value of r, which is 0. So we have our new an equal to n minus 3 over n times n minus 5, an minus 1. So substitute the value of n equal to 1. So we have a1 equal to negative 2 over 1 times negative 4, a naught. So we have 1 over 2 a naught. Okay, n equal to, we have a2 equal to negative 1 over 2 times negative 3a1, substitute a1, we have a2 equal to 1 over 12 a naught. Okay, and n equal to 3, the same goes here, substitute the value of 3, we have a3 equal to 0. And for n4, since a4 need to multiply with a3, which is 0, it will be 0 again. So for n equal to 5, a5 is equal to 2 over 5 times 0, a4, which means here we have the indeterminate form. Indeterminate form. Since it is an indeterminate form, it will be case 3a, 0 over 0. Okay. Therefore, a5 here does not equal to 0. So it is another arbitrary constant. Okay. The reason, as you can see, we have a5 equal to 0 over 0. So that means we bring 0 to the left. We will have 0 times a5 equal to 0. So 0 is equal to 0. That's why a5 here does not equal to 0. Okay. So next. Continue on. Continuing, we will have n equal to 6 equal to a6, 3 over 6 times 1, a5. That means it will remain as in terms of a5. And n equal to 7, it will be 2 over 7, a6, which means we will have 1 over, substitute a5, a6 here, 1 over 2, a5, and hence we have n equal to a7 is equal to 1 over 7, a5. Okay, so we have y equal to summation n equal to 0 to infinity, an x power of n plus r. So s plus r ni, we can factorize, right? So here we go, we have x power of r, open the bracket, a0 plus a1x plus a2x squared plus until infinity. So next, here. Okay, it will be, substitute all the value of coefficient that we have obtained earlier. That means a0 is a0, a1 is 1 over 2 a0, a2 is 1 over 12 a0 x squared, and then a3 is 0, a4 is 0, a5 is another arbitrary constant, so it will be a5 as it is. So a5 x power of 5 plus 1 over 2 a5 x power of 6 plus 1 over 7 a5 x power of 7 plus until infinity. So here you just need to factorize a0 out and a5. Okay, we have a0 in bracket 1 plus 1 over 2x plus 1 over 12x squared. So it ends here because after this you will continue for a5. So plus a5 x power of 5. Okay, it's not 1, okay, x power of 5. And then 1 over 2 x power of 6, 1 over 7 x power of 7 plus until infinity. Okay, that's it for case 3a. Okay, thank you.